Hello and good morning. We have reached our last set of notes on our third chapter, Electrons, looking at atomic absorption and emission, line spectra, and the chemical composition of stars. The part of the stars in the beginning of this is kind of a little FYI. I'm going to go a little on the quicker side of that. You can always watch it and hit pause and look more into it if you'd like. So obviously we got to figure out where these elements came from. Ultimately, Big Bang Theory, not the TV show, but the real world aspect of it. A lot of information on this slide, so again, please come back and check it out. Big Bang Theory also kind of suggests, what's going on as things have developed over the years when the world was created compared to the universe and everything else. So, come back, check it out. Little flow chart, if you will, on the Great Explosion, the Big Bang Theory, to where all these elements ultimately came from and how they appeared on the planet. Other life cycles of a star, different layers of what's going on, and how stars end up getting these elements and how they're forming, and ultimately, again, reaching us on the planet. A lot of cool pictures that different things that the Hubble telescope, as well as other ones, have picked up far, far away in galaxies. Yay, Star Wars reference. So, how do we know which stars have which elements? Ultimately, there's got to be some way to identify the elements, which is our ultimate goal. So, what we can do is analyze the wavelengths of light. All colors that we see and different shades have different wavelengths. Wavelengths are what control the color of light that is seen, as well as everything on the EM spectrum, electromagnetic spectrum, from microwaves all the way to gamma rays, visible light, kind of in the middle, but ultimately controlled by the wavelength. So for absorption, if you give an atom energy, the electrons can actually be pushed up to higher energy levels. So most things are in a ground state. We heat it up, use a blowtorch or add some energy of somehow, and electrons can jump to higher empty orbitals in higher energy levels. They can jump anywhere they please as long as it's empty and not occupied by another electron. Well, we've heard the lovely statement, what goes up must come down. Electrons want to stay home. They don't want to be gone for long. So they want to go back to where they came from, ultimately Aufbau principle, lowest energy, so it'll fall back down to where it originally came from. As you can see on the right-hand diagram, let's just say an electron originally was in level 1, it jumped to level 2 when it absorbed energy. Well, eventually it will fall back down to level 1. The energy it loses in the form of light is equal to the energy gained. So there's no net loss or gain of energy. It gains X, it jumps up to a higher energy level. When it falls back down, it loses the same amount of energy it gained. And when it falls, light is given off that we can see. HV equals energy. Actually, it's H nu, frequency. Fancy V, if you will. And that frequency, ultimately controlled by the wavelength, is the color. So there's lots of ways to kind of draw this and get an idea of what's going on. In the top image, electrons are going up, gaining energy, going to a higher energy level. and then it falls back down. So when it falls back down, we get light in the form of photons, little packets or a particle of light. Now, light can be particle, like a photon, but light can also be waves. It has this lovely duality nature to it, where it's seen as both a particle and a wave at the same time. Don't worry about that. It's more of an FYI, but it does exist. The bottom image, we've kind of seen half and half broken up. The absorption of energy, excited state. So when electrons are in their normal configuration, according to the Aufbau principle, it's in the ground state. When you add energy to it, those electrons become excited. And then it falls back down, and the emission is when we get the light that we can see. Ultimately, you got to hit that number spot on. If you don't give it enough energy, then the electron does not go all the way to where it needs to be considered in the excited state. Therefore, it just hangs out. No light is released. We can't see anything. Nothing actually happens. So you got to hit that minimum amount of energy needed in order to get the electron into the excited state to whatever energy level it's going to go to. Again, electrons do not have to jump just one energy level. They can jump multiple energy levels. It kind of just depends on how much energy it gained and what that minimum number it needs to get in order to change energy levels. So energy is released during emission. We've talked about this. Not all of the light we can see, only actual visible light. So right in the middle is our electromagnetic spectrum. As we talked, we have radio waves being the very longest wavelength, crest to crest of the curve, all the way to gamma rays. Very, very short wavelengths, high frequency, very, very energetic and small. Energetic and large, sorry about that. The energy it is. But right kind of in the middle is our visible light, also known as Roy G. Biv. Hopefully you all have met Roy G. Biv. Comes around usually when it's raining outside and the sun is still out. You look up in the sky and you can see Roy G. Biv. Awesome guy. But ultimately, the amount of energy given off in the emission depends on which energy levels the electron is falling from. So there's multiple falls that can possibly occur in any given atom. So as we can see with a bunch of these things on the left-hand side, these series, don't worry about knowing the names. They're irrelevant to your world. But the Balmer series, for example, is one we can actually see. So things falling from 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, and actually everything in between, depending on what element you're looking at. The energy and the color of light ultimately will change based on the element that you're dealing with. The amount of energy obviously is going to be different because there's a different amount of energy between energy levels. The distance from energy level 1 to 2 is different in the distance of 2 to 3, 3 to 4, and so forth. Larger the distance, greater the energy, different color of light that can be seen. Questions so far? So the energy spectrum, we can measure the exact wavelength and it can tell you how big the energy gap was the electron fell from. So based on the amount of energy within the visible range, here again our Roy G. Biv, red is of low energy, the V, Roy G. Biv, violet or purple, is high energy, again within the visible light spectrum. We're not worried about outside the visible light spectrum, only within it that we can actually see with our eyes. So This spectrum that we're talking about is basically like a fingerprint. All elements have a different spectrum. Just like all elements have a different number of protons, its identity or its DNA, this is our fingerprint on the type of spectrum that you can see, both in the emission or release of energy or the absorption. For example, here we can see hydrogen and neon and iron. A lot of different colors going on here. Hydrogen seems to only have 4 according to the diagram. Neon's got a lot more, and iron has got so many more. Again, each of these bands of color correspond to a different electron falling from higher energy level to lower energy level. So going a little bit more into it, see a different picture, we can see like a different image, hydrogen compared to helium. That's an interesting one because hydrogen and helium, they differ by 1 electron and 1 proton. Yet helium's is very different. Then you get to neon. Sodium is way bigger, but only has 3 lines that show up. Mercury, again, another one that very different. So every single element is going to have different types of emission spectra. The fingerprint, the ability to identify what element it could be. So we got a couple of ways we can look at this. You take something very, very hot and you throw it through a prism, so the light is then separated, and you get your colors. Or you can do it from a cold perspective, and things can be absorbed, and you actually get a different type of spectrum that is displayed. Either way, we're still able to identify elements, or unknowns, if you will, through this. Now, this ultimately only works with 1 element. So if you have a mixture of elements, this isn't going to work too well because they both give off different color bands. And if you don't know which one corresponds to which, this is not going to work. You got to have only 1 pure element in the gaseous state, because you can't really do this without being in a gas, for it to work. So for our activity that we're going to ultimately do is we're going to do flame tests. Now, notice here in the image, we're not seeing those interesting bands, those individual colors. We see 1 solid color. Well, our eyes are not able to break the colors down into its individual components based on what the electrons are doing. So we can use flame tests to get an idea of what's going on with the element in question. So that's one way of doing it. But you look at lithium and you look at strontium, top left and bottom row 1 in, they both have that reddish color. Yeah, lithium is a kind of a more crimson red compared to strontium, but you can come across elements that are similar in color, where you would actually need a spectroscope in order to separate it into its line spectrum that we've already seen. But for our experiment, again, we're doing flame tests, so we'll be able to see what's going on based on just a singular color. And we want to use our best ability to identify that color. So not just, it's red, it's yellow, give something else to back it up with. Now, you guys are familiar with fireworks. Fireworks are ultimately controlled by the chemical composition of the firework. Depending on what you use, you can control what colors you see. So again, our white, silver, blue, red, green, yellow, purple, orange, different things, sodium, barium, strontium, titanium, copper. You want to be a pyrotechnician later on in life. You got to know a lot about chemistry in order to control the colors that you want to show in your fireworks display. Kind of a cool job, I would think. So normally, with regular light, you see a continuous spectrum, also known as a rainbow, or Roy G. Biv. That's just regular white light. Now, from an emission spectrum, when you get a element, a sample of gas, you're going to apply some electricity, give it some energy. The electrons do their thing. They go up to the excited state. They fall back down, back and forth, over and over again. And you get your emission spectrum. Black background, colorful bands sitting forefront. An absorption spectrum, same thing you see. Bottom and the top one are the same element, but notice we see Roy G. Biv in the background, but there's some bands that are missing. Those are specific wavelengths. That's how we can identify an unknown, because we've already created the emission and absorption spectrum for every single element. Therefore, I have to match the wavelengths based on their number, and which ones are there. I can identify an unknown. Kind of cool stuff. So these absorption lines, again for stars, the colder outer layer of the stars absorb the energy from the hotter inside of the star, so we can see the absorption lines. So it's those lines that matter. Those direct, definitive lines is what helps us identify one element from another element. That's our goal, identifying an unknown. That's what we want to do. So just kind of showing you different ways of seeing different energies with spectrum. Again, they're wavelengths and angstroms. If you've never heard of angstroms, it's 10 to the minus 10 meters. The symbol is the letter A, capital A, with a degree symbol, the little circle, on top of it. That's an angstrom. All right, thank you very much. We shall move on from here.